ballistic rocket of the German V-2 type. North American's test instrument vehicle, the Native, is illustrative of this class. This small ballistic missile with a range of 35 miles was launched at Holloman Air Force Base. At long ranges, the ballistic rocket presents many problems. In consideration of time schedules for development, North American aviation has taken a more conservative approach. Development of the Navaho series of missiles began with studies of the glide rocket, which was essentially a B-2 with wings. The missile was to be ground-launched, and after a ballistic ascent and partial descent, was to glide 500 miles to the target. At this stage in the program, a review by the Air Forces resulted in an increase in the range requirement. Limitations on range of the glide rocket are similar to those associated with the ballistic type. Studies of the problem reveal that for longer ranges, it would be necessary to add high-speed engines for cruising. Accordingly, ramjets were added to the Navajo design, and the Air Force designation of XSSM-A2 was applied. With this configuration, the missile would be boosted to supersonic speed by a self-contained booster. Then the ramjets would permit the missile to cruise to the target. This type of missile presented many advantages. Most of the flight path was flat, and accelerations were much lower, which presents a simpler guidance problem. The speeds encountered permitted use of known techniques of airframe manufacture. The only disadvantages to this design were restrictions of range due to weight of the internal boosters. As the guided missile program advanced, requirements were established with an ultimate goal of 5,500 nautical miles. Realizing the practical aspects, the Air Force set up intermediate requirements. North American has divided the development into 3 phases. Phase 1 concerns the development and flight testing of a turbojet-powered test vehicle with a configuration which closely approximates the ultimate long-range missile. The test version has been designated the RTVA-5. Phase 2 is the development of an operational missile, which is brought to cruising altitude and speed by a disposable booster. Ramjets will supply cruise power for a range of 3,600 nautical miles. This missile is designated the XSSM-A4, code word Navajo 2. The Navajo 3 will meet the ultimate objective of a range of 5,500 nautical miles by changes in structural material, by the increase in flight speed, and through the incorporation of other late developments. Preliminary design of the RTVA-5 was completed in September 1950. Detailed design and manufacture of components is underway. Preliminary and some detailed design of the Navajo 2 and its rocket booster are well advanced. The Navajo 3 is still in the preliminary analysis phase. Another important task of the preliminary analysis section concerns operational analysis. A strategic missile must be carefully studied to assure most effective employment. Present studies are based on the combat use of the Navajo 2 and include quantities required, storage, maintenance, transportation, handling, and launching. In addition, the number of technical personnel and their training are also under study. Activities on the MX-770 project are further divided into aerodynamics, airframe, guidance, and propulsion sections in North American's Aerophysics laboratories. Aerodynamics covers all phases of theoretical analysis, trajectory calculations, aerodynamic design, and long-range missile studies. Experimental supersonic research is conducted at several facilities. Since September 1950, wind tunnel tests have been made of the RTVA-5 configuration at Mach 0.35 to 2.87. The vertical stabilizers and rudders are mounted on the nacelles to place the surfaces outboard of the trailing vortex pattern from the front surfaces, thereby ensuring positive static directional stability under all flight attitudes. The model shown here is referred to as the RTVA-5 stability model. The purpose of the stability model is to provide aerodynamic information for the determination of component air loads and to provide stability and control data to be used for the design of the autopilot. Here is a typical Schlieren view which indicates the complexity of the supersonic flow. In order to obtain experimental performance data for a normal shock side inlet diffuser, such as that being considered for the RTVA-5, tests were conducted on this 04 scale duct research model. In the test missile, the air entering the diffuser will be conducted through subsonic ducting. The boundary layer is removed by an auxiliary duct simulated by this curved section. The model provides for inlet testing with an ideal subsonic diffuser in the presence of the forward surfaces and fuselage. To avoid interference in flow caused by the forward control surfaces and to provide better entry at positive fuselage angles of attack, the diffuser inlet is canted down 6 degrees with reference to the fuselage axis. The boundary layer and air entering the normal shock-type diffuser will be shown in the Schlieren view. A .11 scale model has been built to test at higher Reynolds numbers. Here is the model in North American subsonic tunnel for low-speed tests. The airframe section is concerned with structural design of missiles and their component parts. Extensive tests are also conducted on new types of construction. This prototype missile wing is of one-spar aluminum alloy construction. Here the wing is subjected to bending moments beyond any actually attained in flight. Tests for aeroelasticity are conducted on metal prototypes when available. For the RTVA-5 and Navaho 2 designs, a model wing was constructed from plexiglass to save the high cost of prototype construction. The Delta Wing plexiglass model was constructed in the Aerophysics Laboratory model shop. A 1/3 scale outline of the wing was marked on this layout table, and wooden blocks were cemented in position to serve as a jig for the parts. The plexiglass skin is 60,000ths of an inch thick. The plastic wing was completed after 380 man-hours of construction. This compares to an estimated 10,000 hours required for a comparable metal model. Next, the wing was moved to the structures testing laboratory and mounted on this test platform. The supports are plaster of Paris molded to the wing contour. Clamped in this position, the wing is free to rotate when loads are applied. After placing lead weights in specific areas, wing deflections are determined by photographic records of 16 dial gauges. Repeated deflections reveal the influence of loads at certain points on the wing. Mock-up of the RTVA-5 design was completed early in 1951. The full-size mock-up is 66 feet long. The delta wing spread is 28 feet. 2 vertical stabilizers and standard rudders are mounted on the nacelle. The tricycle landing gear will permit tests to proceed in a manner closely related to airplane flight testing. The main landing gears retract inboard into wells below the body. Operation of the landing gear will be controlled from the ground by radio command signals, which will start a pump motor on one engine and will also position the selector valve. The landing gear will be operated by a 3,000 pounds per square inch hydraulic system. Light gauge stainless steel will be used to form most of the skin and structural details of the body. Internal structure is shown on the left side of the mock-up. The RTVA-5 will have an airframe structure weight of 10,500 pounds and a gross takeoff weight of 35,000 pounds. The forward ogive will contain 1,300 pounds ballast. Next is the guidance compartment, containing provisions for the power supplies, computers, and the stellar supervised auto navigators. The forward fuel tank has a volume of 76.2 cubic feet. In this test vehicle, the warhead compartment will contain the essential components of the telemetering and radio control equipment, plus space for the nose wheel and retracting mechanism. The afterbody contains fuel tanks with a combined volume of 426 cubic feet. The stainless steel tanks will be seam welded to ensure leak-proof joints. The RTVA-5 is powered by 2 Westinghouse J40-8 turbojets with a takeoff rating of 10,900 pounds thrust. A mocked-up engine has been modified to comply with the RTVA-5 configuration. Structural and clearance problems have been determined with all accessories added to the engine. With a portion of the rear of the nacelle removed, the complete engine, including afterburner, is rolled into position. An integral track permits complete accessibility for engine changes. Cooling and scavenging of the engine is accomplished by the boundary bleed from the inlet scoop. Flight tests are scheduled for September 1952. The most complex problem facing a missile designer is the development of an accurate long-range guidance system. The electromechanical department is developing a guidance system for the Navajo 2 and 3. Another segment of this organization is preparing radio control and telemetering for the RTVA-5. The first models of the RTVA-5 will be capable of taking off from the ground, cruising, and landing under the influence of radio control. Later models will be guided by a self-contained auto navigator which is stellar supervised. This is the forerunner of the long-range guidance system for the Navajo. For test purposes, a multi-channel telemetering system will be used to transmit flight conditions from the airborne RTVA-5 to a ground station. The airborne equipment utilizing this laboratory vibration simulator transmits intelligence to the ground station, where meters furnish instantaneous readings and a tape recorder produces a permanent record. Control surface position, hinge moment, acceleration, temperature, and pressure are telemetered simultaneously from the missile. The telemetering trailers are being prepared for equipment which you saw under test in the laboratory. Radio supervision will be performed from these two trailers, which comprise an MSQ-1 control unit. In the radar trailer, the missile is tracked in flight out to a range of 200,000 yards. Intelligence from radar is sent to the command trailer, where the flight path of the missile is traced on a plotting board. The command trailer is the operational center for activities connected with flight of the missile. The operator traces the flight path and puts in course changes as needed. In December 1949, the first step in the development of the auto-navigator system for the Navaho 2 series of missiles was taken when the Aerophysics Laboratory completed the Mark X-1 auto-navigator and initiated laboratory tests on the system. Platform drift was amplified by motion of a light beam reflected from mirrors on the platform. The platform assembly was mounted in a large bowl so that angular movement about all axes would be produced with no linear action. Tests on a vibration stand produced similar results. In March 1950, the first series of laboratory tests were completed and indicated that the auto-navigator was capable of directing over 50% of hits within a radius of 2,500 feet at the calculated missile range. Flight tests were initiated in April 1950, the first flight test ever conducted on a purely inertial auto-navigator. The stabilized platform is the main component of the auto-navigator system. The platform is supported by air-lubricated bearings at a large central ball. Three large gyros, which are mounted in air-lubricated precession axis bearings, are used to maintain stability, one gyro for each axis of rotation. The platform is used to orient two distance meters, which measure range distance and lateral departure from the flight path. These laboratory racks contain components of the auto-navigator electronics and test equipment. Regulated power supplies are provided for the gyros, servo motors, and electronic equipment. The gyro control system contains a power supply and indicators for gyro speed and voltage phase differences. A system of computers supplies earth rate torques to the gyros and also supplies torques to correct the output of the distance meters. These racks are of full laboratory size. Naturally, a missile-borne system will of necessity be much smaller. North American is engaged in a program of miniaturization to reduce electronic component sizes. This normal size amplifier will be replaced by a miniature size amplifier. Or, as a later development phase, may be replaced by this sub-miniature size. The platform assembly was designed for a vertically launched missile and allows 180 degrees pitch freedom and 30 degrees freedom in roll or yaw. To permit the airplane to make complete turns, a rotatable base with azimuth follow-up was provided. The flight test subjected the auto-navigator to a series of environmental runs. airplane enters a turn, the action of the stabilized platform is apparent. The platform seems to rotate, but actually the platform maintains a constant position while the airplane turns about it. The airplane was flown to maintain a course dictated by the autonavigator. A ground mapping camera was used in conjunction with a recording camera, which photographed counters in the computer unit. Correlation of the data established the error introduced by the autonavigator. The test showed the pure inertial autonavigator was satisfactory for flight times under 1 hour. Tests of the autonavigator show that with gyro stabilization alone, the error in the flight path of the missile would increase with time. However, when a stellar supervisor is incorporated in the autonavigator system, the error accumulates more slowly. A stellar supervisor was mounted on the stabilized platform, and laboratory tests were initiated in May 1951, marking another major step in the development of the autonavigator system. The new system is known as the Mark X2. In this laboratory test, a light mounted in the black circular disc simulates a star. The telescope tracks stars automatically, even in bright sunlight, and checks the orientation of the platform so that random, unpredictable drift will be restricted to small values. In operation, the telescope is flued at programmed time intervals from one star to another. Due to its large field of view and also to its sensitivity to faint stars, the stellar supervisor makes possible navigation to any position on the Earth at any time. The colored pins indicate the stars which can be tracked, and the plastic disc indicates the field of view which can be covered by the telescope. The Navajo 2 will contain a stellar supervised autonavigator similar to the laboratory model to guide the missile to a range of 3,600 nautical miles with an error of not more than 1,500 feet at the target for 50% of the missiles launched. Components for the autonavigator are checked thoroughly before being accepted. The gyro operational test stand is used to determine the merit of gyro rotor bearings during run-in tests. As many as 3 gyros can be tested simultaneously. To reduce windage loss, the gyro rotors are operated in an atmosphere of hydrogen at a pressure of 6 centimeters of mercury. Determinations can be made of electrical power, mechanical power, acceleration time, temperature, and rotor speed. A torque tester is used to determine the performance of the gyro air bearings on the output axis. The gyro is rotated to different positions, and readings are taken of the unbalanced torque about the output axis. The torque tester is also used to determine gyro balance and spring rate. A gyro arrangement called the Navaho was designed to reduce the drift error which is produced by a single gyro. 2 gyros are mounted on the test stand and operate as a pair. The gyros reverse their direction of rotation periodically. Any disturbing torques which affect the gyros tend to produce equal and opposite effects on each gyro, and thereby drift errors are canceled. Thus, the combined performance of the pair is superior to that of either gyro individually. An autopilot will position the control surfaces of the missile. To determine the stability of an autopilot-controlled missile during flight, the Reeves electronic analog computer, commonly referred to as the REACT, is used. Flight equations are set into the computer to simulate conditions which the missile will encounter in flight. Disturbances such as wind gusts, engine failure, and controlled surface misalignment are imposed upon the flight equations. The effects of those disturbances on the performance of the missile are sensed by the autopilot electronic system, which is simulated here in the form of breadboard assemblies. The autopilot system controls the hydraulic servos to position the controlled surfaces and correct the flight path. The resultant performance, as well as the action of the controlled surfaces, is then recorded. In airplanes, movable control surfaces are generally mounted on hinges and are controlled by bell crank actuators. The thin surfaces used in the guided missile led to the design of this rotary actuator. The rotary actuator moves the control surface, simulated here by the leaf spring arrangement, and also serves as a hinge with the additional advantage of being free from backlash. Major effort of the propulsion section is directed toward the development of a rocket booster for the Navajo 2. Development status of the booster power plant, Air Force designation XLR-43NA1, is well advanced. The power plant developed 75,000 pounds thrust for 56 seconds minimum. Alcohol is used as fuel and liquid oxygen as oxidizer. Here's a schematic of the power plant. The fuel and oxidizer are forced at rated flow into the rocket thrust chamber by a turbo pump driven by high-pressure steam produced by the gas generator system. Gas to drive the turbine is produced when concentrated hydrogen peroxide stored in this tank is forced under a pressure of 450 psi through a cobalt-plated screen catalyst in the decomposition chamber. The chamber consists of two stainless steel shells which house the catalyst pack, consisting of 36 cobalt-plated screens. Gases from this generator drive the turbo pump, one of the major components of the rocket power plant. A two-stage turbine wheel applies power to drive the oxidizer and fuel pumps. Exhaust steam from the turbo pump is further utilized before expulsion by passing through a heat exchanger. Another important component of the rocket power plant is the main oxygen valve, located below the turbo pump. This lightweight valve features a three-position butterfly, low pressure drop, and compact size. Two main alcohol valves are flange-mounted to the nozzle inlet of the regeneratively cooled thrust chamber. The valves are solenoid-controlled, pneumatically actuated for positive control of fuel flow. 750 psi regulated pneumatic pressure supplied from 3,000 psi helium containers is used to operate the control valves. Reduced pressure is used to pressurize the alcohol, oxygen, and peroxide tanks. The rocket thrust chamber is basically a straight sleeve attached to a throat by a convergent section and flares out to form a nozzle exit. A chamber-to-throat area ratio of 2:1 is employed in this unit. The fuel and oxidizer injector is of the doublet impinging stream type, selected for its proven reliability in use with alcohol liquid oxygen motors. The fuel mixture of alcohol and water first enters through a manifold at the nozzle end, flows axially through the motor between the inner and outer walls, and uniformly enters the propellant injector, and then flows through the injection orifices into the combustion chamber. 6% of the fuel is injected through radial holes in the inner wall of the combustion chamber to provide film cooling, which augments the regenerative cooling. Liquid oxygen is fed to the center of the injector and flows around the radial alcohol passages to the rear of the injector face and through the injection orifices into the chamber where combustion takes place. The 75,000-pound thrust chamber and injector combination was subjected to a comprehensive static test program to assure performance and reliability. Initial investigations were made to determine suitable ignition and starting conditions. In these tests, propellant tanks located in the large test stand are used. A gaseous nitrogen pressurizing system forces propellant into the combustion chamber where they are ignited and fired. More than 50 firings were made at 75,000 pounds thrust. Many runs exceeded 60 seconds duration, proving the thrust chamber assembly capable of reliable operation in the rocket power plant. To further prove operation of the thrust chamber assembly, the unit was mounted in a horizontal test stand. Firings in this stand have proved very successful, and runs under various extreme conditions are being made. For example, early in May, 2 runs exceeded 90,000 pounds thrust and 60 seconds duration. Maximum thrust was 94,000 pounds. In run number 13, the highest known impulse, a total of 5,980,000 pound-seconds, was achieved. The horizontal firings are made at night to permit full use of the vertical stand during the day. The flame extends more than 100 feet. rocket power plant assembly, consisting of pre-tested components, is operated in combination for the first test in a special preparation stand where the system is instrumented for combined electromechanical checkout and calibration. One of the first tests conducted in the calibration stand is a complete electrical check of all instruments and circuits. This is followed by a series of flow tests, starting with water and then using actual propellant. Large pipes transfer the fuel to a collection tank and the oxidizer to a remote drainage area. On completion of the calibration stand test, the thrust chamber and propellant injector are installed. Then the rocket power plant in its test firing cage is swung over to a large vertical test stand. A shipyard gantry crane on rails is used for this purpose. The test firing cage contains two heavy-duty stainless steel tanks, which provide a full supply of fuel and oxidizer for power plant operation. The entire power plant assembly closely parallels a missile configuration. The cage supporting pads are attached to a large calibrated thrust beam. Working platforms can then be swung into position. Firing of the complete rocket power plant differs from runs with the chamber assembly alone. In the power plant tests, the propellants are supplied by the unit's own pumping system and tanks. Thus, the rocket power plant is a completely independent system. In operation, the following takes place. After the alcohol and liquid oxygen tanks are filled, the propellants are pressurized to approximately 21 psi. A separate igniter is used to initiate combustion in the chamber. When satisfactory igniter operation is observed, the main propellant valves are open. During this phase, the propellants are under about 1/10 flow and provide even burning in the combustion chamber. This is called preliminary burning. Full thrust operation is initiated by opening the peroxide valve and allowing flow from the pressurized hydrogen peroxide tank to the decomposition chamber. Steam pressure is applied to the turbine, and in approximately 7/10 of a second, the alcohol and oxygen pumps are at rated RPM. Simultaneously, the main oxygen valve is fully open. Propellants flow at the rate of 2,600 gallons per minute to the rocket chamber. Firing preparations include check of instrumentation and control circuits, operation of the pneumatic system and mechanical components, and special items according to test procedure. After loading propellants, the work platforms are swung out of the way. In the control center, 500 feet away, the firing operator is stationed at an electrical sequencing panel. Timers and relays control ignition, opening of propellant tank valve, and the hydrogen peroxide tank valve. The operator presses the launch start button, and the unit automatically sequences tank pressurization, igniter, and the main propellant valve. Preliminary burning, okay. Main stage. American static test program has proved that the rocket power plant meets or exceeds the design specifications. Preliminary design and some test work is now underway on a 120,000-pound thrust system for the Navajo 2 booster.